Welcome to the next video in this unit. We're going to talk a little bit more about graphing rational functions. We're going to talk about horizontal asymptotes, finding x and y intercepts, and talk about the behavior that a rational function has around the asymptotes, either vertical or horizontal. Okay, as you recall, a rational function has most of the time, it has both a vertical asymptote and a horizontal asymptote. So if you were drawing just a graph of just your basic rational function, you remember that it has a vertical asymptote. It could have more than one vertical asymptote. And then it has one horizontal. The basic 1 over x graph looks like this, right? So one way to determine where or if it has a horizontal asymptote is this method here. And so you can see that you have a rational expression. It has a numerator and a denominator, a polynomial in the numerator, polynomial in the denominator. So one of the first instances here is if I had a rational expression where I had the highest power. I look for the term with the highest exponent, and I compare it to the term in either the numerator or the denominator with the highest value. So for instance, you see that x to the third resides in the denominator, right? And so in that case, it would have a horizontal asymptote where y, and it would be the x-axis. It would be y equals 0. Another case would be is if it had the highest power was in the numerator. If the highest power is in the numerator, there is no horizontal asymptote. All right, so the third case is if it's not bigger on the top and it's not bigger on the bottom, then it's got to be the same. So in the instance where it is the same, like say for instance 2x to the third over 3x squared, to the third, they were the same, then you would have an asymptote at y equals 2/3. In other words, you could cancel them out, and there would be 2/3 left, so it'd be y equals 2/3. So that's a real simple way to determine the horizontal asymptotes. So it's pretty easy to see that if you had y equals 2x squared plus 1 over 5x squared minus 1, that you would just look here at the term with the highest. The rest of this we would ignore. I'm just going to ignore the rest. And I'm analyzing, well, if they're the same, then this would be y equals 2/5. So that's pretty easy to do. The part that's hard to remember for most students is if it's big on bottom or big on top. So if the highest exponent is in the numerator, you have no asymptote. But if it's in the denominator, y equals 0. So when you come to class, I will tell you how the Dolly Parton method helps you remember that. Okay, so finding x-intercepts and y-intercepts. You can see I've got the screen set up. I have y equals 2x minus 1 over x plus 2. And just as a reminder from the last screen, there would be a horizontal asymptote at y equals 2, because the highest term in the top and the bottom are both x to the first. So you would just have 2 over 1, and that's your horizontal asymptote. To find an x-intercept, you're going to set the numerator equal to 0. So the numerator is 2x minus 1. I set that equal to 0. That's 2x equals 1, and x equals 1/2. So where x is equal to 1/2, that is the x-intercept. That's where the graph crosses the x-axis. Okay? And then for a y-intercept, you're going to let the whole thing be equal to 0. No, I'm so sorry. That's not how that works. You're going to actually let x be 0. If it's a y-intercept, right, x is 0. So I'm going to put a 0 in everywhere that there's an x. And that's going to be 0 over -1 over -1, which is 1. So this is going to be 0, 1 is going to be the y-intercept. And that's how that works. So rational functions behave a certain way at the asymptotes. And so, like for instance, when you're talking about a vertical asymptote, which you can see this one right here, straight up and down, that you know that as this graph comes from the right, it goes to infinity. But as it's coming from the left, it's going to negative infinity. So in other words, it's going opposite directions. And we've talked about this just a little bit before. The other thing, though, that there is behavior at, that's at the vertical asymptote. So they're usually going the opposite direction. Occasionally they'll go the same direction when it's a perfect square in the denominator. But at the horizontal asymptote, on the other hand, we can see that as x, as the x values approach infinity, positive infinity, as they go this way, the y values are coming down and they're getting really close to, f of x is getting really close to 0. And then on the other hand, as x approaches negative infinity, goes that way, then f of x is also approaching 0. So the behavior at the horizontal asymptote is at y equals 0, which kind of makes sense. As it goes this way, the behavior gets really close to it from the top. As it goes this way, it gets really close to the horizontal asymptote from the bottom. But they're going different directions, but they end up at the same y value. So once again, here's a little bit more complicated graph, and I wanted to show you what this looks like. So first of all, what we notice here is that when you factor the numerator and factor the denominator, nothing simplifies. So there are no holes. There are no holes. But remember that we cannot divide by 0. So in this instance, there are going to be two vertical asymptotes, two discontinuities. So this one will be at 3, this one will be at -1. You can see here discontinuities. And then if you'll notice as you go along here, here is -1, and here indeed is a vertical asymptote. Okay, and so we notice here that this is not a perfect square, so the behavior is that it goes up on one side of it and down on the other. They're opposite directions. And so the other asymptote is at x minus 3, right, at positive 3, and you can see here once again it goes above, one goes one direction and one goes the other direction. Now, if we needed to find a hole, there's no holes. The horizontal asymptote, once again, you've got 3x squared and x squared. Notice I'm just kind of ignoring the rest of this. I'm just analyzing the highest power in the numerator and the denominator. So the horizontal asymptote is going to be at y equals 3. So I look here, sure enough, there it is, y equals 3. Okay? If I was looking for x-intercepts, if you look here, how many places does this graph cross the x-axis? Well, 1, 2 places. So remember that we would set 3x equal to 0, we would set the numerator equal to 0, x minus 4 equals 0, so I would have an x-intercept at 0, 0, and I would have an x-intercept at 4, 0. Well, do I? Yes, I do. Right there and right there. Does it cross the y-axis? Well, here's the thing. If it crosses the x at 0, 0, it is also going to cross the y at 0, 0. So that is going to be automatically your y-intercept. And there will only be one y-intercept. As you can see here, there could be more than one x-intercepts. Now, here's another thing on here that I want to point out before we wrap this up. But you can see the horizontal asymptote. And you've been taught that an asymptote is a place where the graph gets close to but doesn't cross. There is an exception, and here it is right here. If I have two vertical asymptotes, sometimes the graph between will cross a horizontal asymptote. So it will fit with the pattern, like it's going up this way and down this way, and it's crossing the x-axis, the x-intercept. Occasionally, it will once again cross a horizontal here, like it will go above it and then just kind of hover. So those are some exceptions. It could cross a horizontal. It doesn't always, but it could. It will never cross a vertical. It never crosses a vertical asymptote. It could cross a horizontal one, but not a vertical one. Okay, this is a lot of information, and we're going to need to practice quite a bit, which we will do in class. So I will see you then.